Good afternoon, dear conference participants. Your attention is invited to work on the topic, Electric Drive of Coordinated Rotation for Mechanisms of Flow Transport Systems. Presently, energy conservation stands as a primary focus of innovative development in the Ukraine and Republic of Kazakhstan. Reflected in the inclusion of energy-saving initiatives in nearly all significant strategic documents. Notably, the industrial sector alone accounts for approximately 70% of total electricity consumption, with electric drives of flow transport systems, FTS, contributing an average of 20%. Flow transport systems typically consist of a series of conveyors, each designed for specific functions such as loading, transporting, sorting, and unloading. These conveyors may include belt conveyors, roller conveyors, screw conveyors, or pneumatic conveyors, depending on the nature of the materials being transported and the layout of the production facility. The frequency method stands out today as the most technically and economically viable control method for alternating current, AC, electric drives. Nevertheless, research indicates that frequency-controlled electromechanical systems utilizing stator circuits, while offering extensive functionalities, pose a technically more intricate challenge for voltage-frequency regulation compared to regulation through rotor circuits. This complexity arises from the fact that the power of a thyristor frequency converter, TFC, is comparable to that of electric motors. Consequently, the advancement of novel circuit solutions for regulating the performance of FTS emerges as a pressing task within contemporary electromechanics. This study aims to design a two-motor electric drive for the mechanisms of flow transport systems with medium to high power, aiming for improved energy efficiency. Slide 4 illustrates a functional schematic of a dual-motor electric drive coordinated rotation featuring a cascade arrangement of two asynchronous motors. In this configuration, the rotor windings of the asynchronous motors are linked in series via a controlled rectifier within the rotor circuit of the first motor and an inverter within the rotor circuit of the second motor, collectively referred to as a thyristor frequency converter. For investigating the dynamic characteristics of the coordinated rotation electromechanical system in flow transport system mechanisms, we conduct computer simulations of a two-motor electric drive setup. This configuration comprises two asynchronous motors with wound rotors, with one motor connected via an asynchronous valve cascade circuit and the other connected through a dual-fed machine circuit. Slide 5 shows a simulation model of a two-motor electric drive corresponding to the functional diagram shown in Slide 4. Computer simulation of a dual-motor electric drive was carried out in the MATLAB system. Dynamic characteristics of a two-motor electric drive obtained at various values beta, opening angles of the thyristors of the rectifier group, are shown in Slide 6. Examination of the dynamic traits reveals a distinction between the second motor, linked via the dual power circuit, and the first motor, connected through the valve cascade circuit, despite identical parameters in the equivalent circuits of both motors. The sliding power directed to the rotor windings of the second asynchronous motor proves inadequate to replicate the characteristics of the first motor. Consequently, an additional power source in the rectified current circuit of the motor rotor is deemed necessary. A functional diagram of a two-motor electric drive with an additional power source in the rectified current circuit of the rotors of two asynchronous motors is shown in Slide 7. Slide 8 illustrates dynamic characteristics of a two-motor electric drive at beta equals 30 degrees and beta equals 60 degrees respectively. As can be seen from the last slides 8. After connecting an additional power source to the rectified rotor current circuit, the dynamic characteristics of the two motors coincide. Thus, during the work, the following conclusions were made. Therefore, employing a cascade circuit in a dual-motor electric drive, supplemented by an additional power source in the rectified rotor current circuit, enables the synchronized rotation of two motors. This synchronization can be achieved not only with identical nominal parameters but also with differing power and synchronous frequency of rotation. The primary advantages of this approach to coordinated rotation in a twin-motor electric drive using a cascade scheme include the capacity to adjust the power factor of the machines. Moreover, it reduces the power transferred to the control circuit by the thyristor frequency converter, thus enhancing the reliability of the electric drive's power components. By regulating the rotation frequency of two AC motors, it becomes feasible to enhance energy efficiency. Thank you for your attention.